Ladies and gentlemen, Microsoft have been hard at work on DirectX 12's latest update, bringing with it new features such as Shader Model 6.8. And this update will be extremely important for developers to get the most out of your PC hardware, not just in terms of the best visuals, but also the best performance as well. But what exactly is Shader Model 6.8? What does it bring to the table? What are work graphs, GPU upload heaps, and a bunch of other technical mumbo-jumbo? Well, I'm glad you asked, and you can probably guess from the title of this video, that's what I want to give you guys a rundown on to really understand why this update is going to be so beneficial to you as a PC gamer. Now, before we get too deep into the weeds here, what I do want to do is just give you a kind of brief history lesson. If you're not too interested in this, or you're very familiar with the updates of Mantle from AMD and the older DirectX 12 stuff, then of course you can skip forward in the video a little bit. But for everyone else, I do suggest you check this out because it's going to give you kind of a better understanding of where we are at now and why we're in this place. So DirectX 12 was actually heavily influenced by AMD's Mantle project, which debuted in 2013. This was a low-level API which also sought to increase multiple CPU cores utilization, as CPUs back then were becoming increasingly multi-threaded. 4 cores, 8 threads were not exactly uncommon for mainstream PCs. Now, Mantle was only for AMD GPUs. It would work for Intel CPUs, of course, but for the actual GPU side of things, you would need a Radeon card to be able to take advantage of it. And we saw it implemented in some Battlefield titles, we saw it in Thief, and honestly, it was very impressive for the time. It reduced overhead for the driver, it basically got really excellent improvements in frame rates, but ultimately, the whole reason AMD crafted this API was to kickstart a push for the industry as a whole to move towards a low-level API, and it did so with DirectX 12 as well as the Vulkan API from the Kronos group. Now, if you want more insight into the Kronos side of things, I actually had an interview with Neil Trevitt a couple of years ago where we went extensively over, of course, the whole initiative of the Vulkan API and how we actually saw AMD's Mantle project really benefit it. But of course, for this video, we're going to be focusing primarily on DirectX 12 and the newest updates. With that said, since its debut, Microsoft's DirectX 12 has undergone several enhancements and improvements throughout the years. The initial release of DirectX 12 had a few critical goals. Much like Mantle, it really was designed to help utilize multiple CPU cores. Now, DirectX 11 technically could handle multiple CPU cores and threads, but, well, it wasn't exactly great at it. Also, it was designed to reduce driver overhead and API overhead, and just generally speaking, become more efficient. More recently, we've also seen, of course, the release of DirectX 12 Ultimate. And this shipped as part of the Xbox Series X API, and we also saw it debut, of course, on PC. Ultimate brought in several new features such as DirectX Ray Tracing, mesh shaders, variable rate shading, and finally sampler feedback. Now, we did see some of this stuff also appear in other APIs. For example, mesh shaders was initially actually a Vulkan extension, and NVIDIA were pushing that with the Turing release. But, well, now, of course, it's part of DirectX. We've also seen Microsoft launch Direct Storage. Now, technically speaking, Direct Storage isn't 100% part of the DirectX API. Instead, Direct Storage is kind of its own API, but as the name implies, it takes over the duties of handling the storage. This is particularly important when maximizing the performance of an NVMe storage device. But the Direct Storage API does liaise with DirectX 12 in a number of instances, bringing your GPU into play. For example, if it needs to decompress some data. Now, of course, I am glazing over a lot of these explanations, but I wanted to really get us onto the same page. If you are a developer, then of course I would recommend you read the various technical blogs, but I've also covered them, of course, in videos, where I, like the dwarves of a certain mine, dug both deeply and greedily. Anyway, subtle Lord of the Rings references aside, let's get back into the newest changes for PC gaming. namely what Microsoft have announced here with, for example, Shader Model 6.8. Officially, AMD support this with RDNA 3 based cards and the appropriate drivers, so you need RX 7000 series. For NVIDIA, meanwhile, you'll need RTX 30 Ampere or later. This is a bump in the hardware requirements we saw with DirectX 12 Ultimate. This, you would need RTX 20. Well, technically Turing could handle pretty much everything aside from ray tracing if you had a GTX 16 series card. Meanwhile, AMD, it was RDNA 2 RX 6000 series. Now, as I kind of alluded to already, I do want to make this video as appealing to a wider audience as possible. I'm going to be taking some technical liberties here or there and snipping down some details. Again, if you are a developer, highly technically minded, consider this kind of a jumping off point, and I would encourage you to do your own research. Naturally, I'll put some links in the video description. But if you just want too long, didn't read, you just want to get an idea of what's happening here, then I'll give you guys a rundown, and it should serve us to get us all on the same page and to kind of be excited for the future. So now we've gotten all of that stuff out of the way, let's get into the technical stuff. And we're going to begin with GPU upload heaps, because it's probably the shortest of the things to go through, and while it's perhaps the easier of all of this stuff to understand, it is also going to serve as the backbone of much of the tech that we're going to be talking about in a moment, because ultimately it allows us to move a ton of data around really efficiently. Now, one of the benefits of a console, let's take the PS4 or the PS5 as an example, is they have a single large pool of memory. The PS4, for example, has 8 GB of memory, the PS5 has 16 GB of memory. Now, yes, some of this memory is cordoned off from games developers, in other words, it's reserved for operating system functionality, but what's remaining is basically accessible for games developers to do with as they wish. This is not quite, of course, how a PC works. So if you have a high-end CPU and a high-end GPU, a discrete GPU, you will basically have, essentially speaking, two kind of separate pools of memory. You will have the DDR4 memory or DDR5 memory, depending on your platform, which of course will be for your CPU, and you will also have the VRAM for your GPU. So for example, if you have an RTX 3080 graphics card, you may have 10 GB of VRAM, and for your main system memory, you could have like 16 or 32 GB, for example. This approach for consoles is very flexible, of course, because if a developer wants to go ham with textures and visual assets, they can, or if they want to instead include other things like perhaps larger maps, audio, NPCs, whatever, they can just do so. But a real big advantage with the unified memory system as well is that data can be accessed by the CPU and GPU, worked on by either, and you don't need to copy data from, say, the system memory to the GPU, or vice versa. There was a lot of talk about this with the PS4's introduction with a unified memory system. You can see a diagram on screen with the PS4's memory with various buses. This is a kind of earlier diagram, so back then the console only had 4 GB, and it was then of course for the retail models upgraded to 8, but basically speaking pretty much the same principles apply, just the quantity of memory has increased. Now for PC gaming, a very important change happened several years ago to help facilitate improvements in this area, well kind of. The access of data between the main system memory and GPU came in the form of resizable bar base address register. This enables Windows to manage GPU VRAM. Now, historically, this wasn't really possible. Well, again, kind of. Before rebar, there was bar, but this basically limited memory to chunks of only 256 megabytes, which, well, if you're dealing with 8 GB or so of GPU memory, it's basically like trying to put out a house fire with a cup of water, one cup at a time. So instead of the CPU being directly able to access the GPU's memory, it would need to basically perform a copy of the data from main system memory to the GPU's memory, traveling via the PCIe bus. So with GPU upload heaps, and again, thanks to resizable bar, Direct3D can basically directly access the GPU memory and copy data from whatever the storage device is to the VRAM or whatever it needs to do. Now this is not always a performance win, and in most scenarios now data just simply doesn't need to be copied. This will help to reduce latency and overhead. There are hardware requirements, not least of which is the stuff to make resizable bar work. For example, a reasonably new CPU and motherboard, and the option in the BIOS. Now, this is where things start to become more complicated as we delve, why yes, both deeply and greedily, okay, I'm going to stop with the Lord of the Rings memes, into work graphs. Now, if you cast your mind back to the debut of DirectX 12, you might recall a lot of talk of execute indirect. This allowed a game to create a constrained command buffer. You can basically think of this for simplicity's sake as kind of like a list of instructions on the GPU to be performed or executed, if you will. Basically, this is processed serially on the GPU. The CPU sends a list of these instructions, an indirect buffer to the GPU, then the GPU processes these commands in, well, a batch. To paraphrase an AMD blog over at GPU Open, the dream of games developers was being given full access to a full GPU-driven rendering solution, where all of the work is done on the graphics chip itself, and it's now here. Now, I'm glazing over this a bit because execute indirect is kind of older. I mean, after all, we even saw it in the preview in 2015's DirectX 12, but work graphs take this principle and modernize it and improve it on several ways. With work graphs, threads can be spawned on the GPU known as producers, and their name is, well, apt because they can produce, if you will, work to run. But this is where things get kind of cool, but also kind of complicated. These newly spawned threads are known as consumers, but a consumer can also serve a dual purpose and can also spawn its own work. So it could basically be a consumer as well as a producer. These tasks are scheduled and can run the moment the GPU has idle time and the capacity to do so. Hence the name work graphs. It's basically a collection of nodes connected by their edges to create a network of nodes. Unfortunately, work graphs are very extensive as a subject to cover, and frankly, getting really into the nitty-gritty of this would become very complicated pretty fast, so instead, I want to focus on giving you a few takeaways. Because the GPU is essentially doing its own management, memory footprints and latency can be reduced. And perhaps even more importantly for the future, CPU overhead can be less important. Now, this benefits PC gaming as well, but potentially, and this is hypothetical because we don't know enough yet about the next generation Xbox, but I would imagine that this would also have some very interesting ramifications for a next generation Xbox as well, because console designs are typically very GPU heavy. If I had to guess, perhaps we would see something similar for the next generation PlayStation console as well, although of course they don't use DirectX, but this is me being, well, I'm just kind of guessing, so who the hell knows. But anyway, to put things into simple terms, work graphs basically group instructions together, and this work can be executed massively in parallel. Parallel computing is, well, something that a graphics card excels in, and so because of this, one set of work can spawn more work as needed. Meanwhile, execute indirect kind of bundles instructions to the GPU, but if anything needs to be changed or adjusted, more instructions are needed from the CPU, so basically there's a lot of backwards and forwards. I'll talk more about the performance and cool stuff in a moment, and yes, it is very impressive. But while DirectX 12 has incorporated a plethora of new technology over the years, work graphs actually, just from the fact that it's, well, so complicated, also needs a few goodies as well. First, we have dynamic shader selection. Now again, falling back to the comparison of execute indirect, information was essentially assigned to the shader by the PSO, pipeline state object. This in turn means however it launched is how it's staying. To put things very simple, you can kind of think of it as like, well, you know what? This is what I was told to do, and that's what I'm going to do. So if it's wrong, too bad, bro. Now, again, of course, I am simplifying things, but you get the general idea, whereas work graphs is much more flexible as a notion. Basically allows one set of work made by the producers to influence work by the consumers, and this cycle can continue. This allows data to flow in a much more dynamic way, and decisions can be made by the code on the fly. There's also implicit micro-dependency model. This seeks to improve the utilization of a GPU by having it less dependent on a group of tasks completing before another one can start. So with a CPU or a GPU, what you want to do is maximize the performance by having it as occupied as possible. So the resources of, let's say, a GPU aren't sitting there doing absolutely nothing for portions of a frame. For example, let's say you're playing a game, Alan Wake 2. Let's say you're targeting 4K, ray tracing, and of course you want high frame rates, right? Who wants to play at 10 frames a second? Of course not, you want the best frames possible. So what this means is you also need to occupy the shaders on your GPU and not have them just be idle at certain points because they're waiting for something else to be completed. Now, broadly speaking, in modern games, the final image which you see on screen, of course, if you're targeting 30 FPS and you're seeing 30 unique frames on screen, 60 FPS, well, it's 60 unique frames on screen, and so on. That's not including stuff like image generation, which is a whole different topic in and of itself. But basically, each of those frames of animation is assembled across several stages. There are a lot of stages, and each one does different things depending on what you're doing, but a few examples could be geometry and depth, calculated textures and lighting and other stuff being done, and, well, yeah, there's also stuff like upscaling as well, which is typically done nearer the end of the rendering process. But this is where things get quite important, because data coherency. What you don't want is for data to get mixed up. Think of it like you're making ice cream but also cooking chicken. Now, what you don't want to do, obviously, is to have uncooked chicken juices mixing on the surfaces, the bowls, and your hands as you're putting ice cream together, because, well, that would just be bad. So in a gaming and rendering context, you can't have, let's say, your ray tracer run on, let's say, a car in a scene if the dimensions of a car, its position, and other objects just aren't decided. Now, the reality is, it's not going to be quite like that. There are other things that's going to happen, and basically you're just going to get errors and things are going to crash and not work too well. But you get the idea. That's why resource barriers are placed to fence off one set of stages from another. So one operation can be completed, and then the next stage can start, and they won't interfere with one another. Work graphs allow a much more fine-grained level of control. You can see that from this graph here. The GPU timeline in the work graph has a lot less idle time. The purple vertical bar in the center of the leftmost shows that, well, if a part is finished, the green, the blue simply cannot start. So let's say the tasking green, say the bottom part here, takes half the time of the green selection. Well, that's just too bad. It doesn't matter. It can't begin because the rest of this stuff has to happen. With work graphs, though, the moment a specific piece of work, the green work, is done, the blue can start and there's just no delay. Basically, the shaders can be as occupied as possible. Now, of course, developers haven't exactly had a lot of time to screw around with this yet, so how games are going to incorporate it, the technology will evolve, and performance comparisons in the real world, it's very early. With that said, during GDC 2024, AMD did host an event with Microsoft. They demoed a scene using work graphs in the form of mesh nodes. This is largely what the name would imply. Work graphs are basically feeding data directly into a mesh shader, so because of this, draw calls can be processed in parallel, and then the rest of the work graph can also be executed. A demo was created to show this off with a collaboration with the Coburg University of Applied Sciences and Arts. Everything within the scene is rendered using a single work graph dispatch, with two exceptions, the UI and the skybox. The buildings, the trees, the foliage, the mountains, everything is done using this technology in the scene. As for the performance, the graph, well, it really does show you how performant this is versus executing direct. Now remember, this is processing time, so in other words, the less time it takes for something to complete, the better. As always though, with both hardware and software, things of course will continue to evolve. In an NVIDIA blog post on work graphs, they said on focusing deferred shading that specifically, for now anyway, a single work graph isn't capable of handling, generating and creating entire frames, i.e. culling, rasterization, a G buffer, lighting, then post-processing and so on. The work graph though can handle many of the steps, but there's still a lot of questions as to how a one graph fits all, if you excuse the turn of phrase, will end up being in the future. Basically, this will cut more and more work from the CPU and push that towards the GPU, so the CPU is instead going to do other things. It's also worth noting, because this statement did fly somewhat under the radar, that Nvidia's CEO, Jensen Huang, believes that in around 10 years or so, as you can see on screen with the quote, traditional rendering is going to just be kind of a thing of the past. Instead, games are going to be using AI. Now, of course, with any new piece of hardware or software technology, it does take developers time to familiarize themselves with it and incorporate it into their projects and game engines, as well as, of course, games that you see on store shelves. And we've seen this numerous times in the past. For example, ray tracing. Yes, it's started out with games not exactly taking full advantage of the hardware, but now we have games such as Cyberpunk 2077 with its path tracing stuff, and it absolutely looks fantastic. And even back in the day, we saw graphics cards like Nvidia's Tesla architecture for the GeForce 8000 series, which of course was a unified design, and initially games didn't really take advantage of GPU compute stuff that much, but now, well, look where we are with stuff like mesh shading and all this other really cool technology, which really is pushing the stuff to the absolute limit. So, yes, eventually speaking, I think AI is going to really change how games are just created, but ultimately this is stuff that, of course, is going to take some years to really incorporate into games. But for now, anyway, for Shader Model 6.8 and all this other stuff that we've been talking about here, it's going to be absolutely fascinating to see how games developers are actually taking advantage of this stuff in the longer term. And I think it's going to be a really good time to be a PC gamer. It will also be very intriguing to see how the next generation Xbox, whatever shape that ends up being, also will use this stuff, because let's face it, you can kind of get a rough idea of what Microsoft are kind of aiming for with the next generation Xbox, just kind of seeing what's happening with DirectX. Now, I'm sure that there is a lot of stuff with DirectX that is certainly not public facing, but yeah, the next couple of years in gaming is going to be absolutely fascinating to witness. With that said, guys, hopefully you found this video informative and fun and whatever else. If you did, of course, leave a like down below, and I'll see you soon. Take care of yourselves. Bye for now.